Hi everyone. So today we are going to start with another new chapter, which is electromagnetic waves. Now this is a very small topic in that sense. The coverage is very what should I say, limited to a couple of areas, but when it comes to JEE mains or NEET, right, this is considered as one of the scoring areas, because you would end up getting some straight questions. From JEE advanced point of view, this is not going to be of much, I don't want to use the word important, but you may not expect questions from this chapter. Okay, so what is it that we are going to cover in electromagnetic waves? So this electromagnetic waves, right, we will start with the idea of the displacement current. So the displacement current is essentially the idea that relates the electric field to magnetic field correlation, like the Faraday's law, right? Faraday's law of electromagnetic induction. What do we learn in that? So we learn that if there is a changing magnetic field means what? It will be giving us a changing magnetic flux. Okay, and changing magnetic flux will give rise to EMF. EMF is voltage only, right? So when there is an EMF or voltage developed, means what? There is an electric field that is getting generated, isn't it? So whenever there is an potential difference, it means what? There is an electric field that is existing over there. Now the other side of the correlation, how a changing electric field can give rise to a magnetic field. So this is something that we will be able to understand through the concept of displacement current. Okay, so first we look at the idea of displacement current, and based on this, right, Maxwell he correlated the equations pertaining to the electromagnetic induction, the entire idea of relation between the electric field and magnetic field, right? So he came up with a set of equations that will correlate the relation between the electric and magnetic fields. So that is the next part, and then we will look at the propagation of electromagnetic waves, because one of the straight applications from the understanding of the Maxwell's formulae, right, is in terms of looking at how the electromagnetic waves would propagate. So we look at electromagnetic waves propagation and also the properties of the electromagnetic waves. Properties means electromagnetic waves would carry what? They would carry energy and they would also carry momentum, right? So how do we measure the energy? How do we measure the momentum associated with the electromagnetic waves? All these things we'll cover. Then we look at the electromagnetic spectrum, and the electromagnetic spectrum will focus on certain important ranges, and these ranges of wavelength or frequencies, right, they would be given specific names, like we'll certain range of frequencies we'll be calling them as microwaves. Certain range of frequencies we'll see all of that, but we will name certain range of frequencies as per a particular pattern, and what we'll see is that depending upon the specific range of wavelength or frequencies, they would have some applications. So we look at what are the applications of the electromagnetic waves. So this is it. So this is what we are going to be covering in this particular chapter. Okay, so okay, Siddharth, you're asking some questions, so I'll just type it over there. Yes, you can see. Okay, so we'll start with the idea of displacement current. Okay, it's a very simple idea. I mean, make sure that you get that idea properly in the first place. So while we are discussing it, right, you try to get that idea properly. If you are not able to understand, means just raise it over here itself so that we can discuss, because this is not a chapter where you would be expected to spend a lot of time. Yes, of course, this the electromagnetic spectrum part and the applications, right? That is a little bit of memory based part. You would have to spend some time to, I mean, not just studying it now or going through it now, but even couple of days prior to the examination, right? You might have to again take a relook at it, because this is a little bit of memory based part that will be involved. Okay, so first we will start with the Faraday's law. So what is this Faraday's law? Faraday's law of electromagnetic induction, right? We have been talking about it very much in the last couple of chapters. So EMI, that is where we have seen this Faraday's law of electromagnetic induction, and the alternating current AC generator, right? AC generator also works on the principle of Faraday's law of electromagnetic induction, right? What is that Faraday's law of electromagnetic induction? When there is an changing magnetic field, of course, changing magnetic field means what? That will give rise to changing magnetic flux. So changing magnetic flux will be developing what? It will be developing an EMF. That is what is the Faraday's law of induction, right? So what is that? The induced EMF is equal to what? Minus d phi b by dt. This is the formula, right? This is what is the formula, no? So this is what is the induced EMF. We have solved a lot of questions on this also in the EMI chapter. Now the thing is, if you look at EMF, like I was mentioning, right, when there is an EMF means what? There is an electric field. So whenever there is an EMF means what? When there is a potential difference, it means what? Through that region there is an electric field. Like, you know, only if it is an equipotential surface, then the electric field will be zero. Correct or not? When there is a potential difference means there will be electric field. So how do we relate the potential difference and electric field? The line integral of electric field will be giving us what is the potential difference. Okay, so we look at this relation. Where does this relation come? It comes in the electrostatics chapter. Where does this relation come? Electrostatics, right? Where we will relate the electric field and potential. We'll be relating electric field and potential. So the line integral of electric field will be giving us what? It will be giving us the potential difference. So since EMF is equal to minus d phi b by dt, what we will be able to see is the line integral of electric field, right, will be related to the rate of change of magnetic flux. So the basic idea we are having, so here we are not going to focus on the numerical level of problems, etc. Okay, the only thing that we are trying to understand is the relation between a changing magnetic field. Changing magnetic field means what? Flux will be changing. Okay, when there is a change in flux means this will be non-zero. This will have some value. This term will be having some value. Means what? There is an induced EMF. Means what? There is going to be an electric field. So a changing magnetic field will give rise to an electric field. And how do we have the relation? We will have the relation in terms of the line integral. So the line integral of electric field will be equal to what? Minus d phi b by dt. Okay, this is what we can call as the, what do we call it as? We will call it as the Faraday's law. What do we call it as? We will call it as the Faraday's law. Okay, like I said, right, this is one part of the story. What is it? A changing magnetic field can give rise to electric field. Now, why are we discussing about this idea in electromagnetic waves chapter? Because we will be able to understand it when we go a little bit further. The propagation of electromagnetic waves, right, is based on the relation between electric field and magnetic field. So Faraday's law gives one part of the cycle, how a changing magnetic field will be able to produce electric field. That part is over. Now here we are going to look at the other part. So what is the other part? Can changing electric field give rise to magnetic field? So can a changing electric field give rise to magnetic field? That is the second part, right? Now this is not only proposed by scientists including Maxwell, but is even proven experimentally. So one of the very common experimental observation is circuit. It's a very simple circuit. Think about a very simple circuit where you have a battery that is connected to a capacitor. Okay, so this is a very simple circuit where we can observe the fact that a changing electric field. So what is the observation we are going to make here? A changing electric field, right, will be giving rise to magnetic field. Okay. Theoretically, a lot of scientists have tried giving this hypothesis. Okay, but this has been even experimentally proven with the help of this very simple circuit of a capacitor connected to a battery. Okay, so there is a battery, there is a resistor, and we are keeping a capacitor. Now we know that capacitor, right, will be what? Charge storing device. So when you connect a capacitor, what is going to happen? This plate which is connected to the positive terminal, this is the positive terminal of the battery, this is the negative. So the plate that is connected to positive terminal will start getting positive charge. Plate connected to negative terminal will start getting negative charge. So the plates are going to keep on accumulating the charge. And in this part of the circuit, there will be a current. There will be a current in the a part of the circuit outside the capacitor plates. There will be current in the region outside the capacitor plates. But what about in between the two capacitor plates? As we know, the medium is generally what? Air or vacuum. We may sometimes have some other medium also, some other dielectric medium also. But in between the capacitor plates, do you see that there will be a current? There will be no current, right? In between the capacitor plates, there cannot be movement of charge from one plate to other plate. That is not going to happen. Okay, so if that has to happen, means we have to have lot of potential difference across the capacitor plates, and we will call it as what? The breakdown. The dielectric medium will actually break down. Okay, that is not going to happen at normal voltage level of operation. It is going to happen at a very, very high voltage. Okay, like typically what happens in thunderstorms, right? What is going to happen? You will see that the dielectric medium, which is the air, the medium will be broken and it will start allowing the charge to move through it. Okay, but normally it will not happen. So we see that this plate is positive, this plate is negative. That is what is going to be the observation. But in between the two plates, there will be no current. Okay. But what is observed is, in between the two plates, right, if you are keeping a simple magnetic needle, like a simple magnetic needle is kept, then what is observed is people started seeing that the moment you connect this particular capacitor to the battery, they started seeing that the magnetic needle is actually deflecting. So when would the magnetic needle deflect? It will deflect only when there is a magnetic field. Otherwise it will not deflect, right? So this is an observation that we have seen in other experiment also. Only when there is a magnetic field, the needle is going to deflect. But what we know so far is, if there is a current carrying wire, if there is a current carrying wire or something, then this can produce the magnetic field, and this magnetic field can deflect the needle. But in the region between the two plates, there is no current that is passing through, which means there should not be a magnetic field. But what is observed is, in fact, there is a magnetic field. That is the reason why this needle is deflecting. So this observation has given the idea to people that the magnetic field can be produced even if there is no current passing through that region. So this experiment proved what? That the magnetic field can be produced even if there is no current through that particular region. Okay, and how do we understand this? Because we are so much used to the idea of magnetic field produced by a current carrying wire. So we say, like, if you have an infinitely long current carrying wire at a distance r from it, the magnetic field produced will be mu naught I by 2 pi r. I hope see, the thing is, we should not forget the formula that you studied in one chapter when we go to other. Like, if you have an infinitely long current carrying wire I, right, at a distance r from it, what is the magnetic field strength? B will be equal to mu naught I by 2 pi r, right? So always, even we have a current carrying circular coil, so we have the magnetic field formula for that. So what is the idea that we are very much familiar with? When there is an current carrying wire or a current carrying coil, it can produce magnetic field. This is something that we are very comfortable, and not just us, but everyone is used to that current will be able to produce the magnetic field. But what we are seeing here is that the magnetic field is getting created in the region between the two plates, even if there is no current over there. Then how do we explain this? What could be the reason for the magnetic field to be produced? If you look at in the region between the two plates, what is there actually? There is no current. There is no current in the region between the two plates. But what is there? There is only one quantity. What is it? Electric field. In the region between the two plates, right, there is only one quantity. What is that? Electric field. And we know the formula also. What is the electric field? It comes in which chapter? Capacitor chapter, right? What is the electric field value? E will be equal to what? Sigma by epsilon naught, isn't it? Sigma is equal to what? Charge on the capacitor plate Q divided by A. So electric field value between the two capacitor plate will be equal to what? Q by A into epsilon naught, isn't it? So this is what is the electric field in the region between the two capacitor plate. The region between two capacitor plate, there is only one quantity that is there. What is it? Electric field. So the magnetic field that is getting produced should be somehow related to this electric field, because there is no other thing, right? There is only electric field, means there is a magnetic field getting created, means this should be somehow related to that electric field. So this is the conclusion that people have come to. Okay, now through the theoretical analysis, right, people could give the relation between the electric field and the corresponding magnetic field that is getting generated. So first thing is the idea of magnetic field getting produced in the region between two capacitor plates, even then there is no current through that region. There is no current through the region, but still the magnetic field is deflecting, means what? There is a field over there that is existing. Somehow we have to explain it, right? When we want to explain it, we will start looking for what is actually there in the region between the two plates. There is only one quantity that is existing. What is it? Electric field. Electric field will be what? It will be normal to the, because you remember the assumptions we make in parallel plate capacitor, right? What is the assumption we make? We will make that, the capacitor plates are pretty large, okay, and the electric field will be what? Normal to the capacitor plate, okay. It will be from the positive plate to the negative plate, it will be normal to capacitor plates. That is the kind of an assumption we make for the parallel plate capacitor, isn't it? So there is an electric field, and the value of electric field also we know. It is what? Sigma by epsilon naught or Q by A into epsilon naught. So this magnetic field that is there in the region between two plates should be somehow linked to this electric field. Okay, so this is the idea that people have come to. Now the thing is, we need to see how this electric field in the region between two plates is linked to that magnetic field, and the relation is what we will be giving by using a quantity or term called as displacement current. See here, before we even start the discussion about the displacement current, right, I want to mention this word. This displacement current is a notional current. Means what? It's not a real current. Notional current means what? This is something that we are going to use to help us explain the observation. That is it. It's not a real current. So when we say that this much amount of displacement current is there, means it is not like the charge is moving through that region. Then we look at the current because of movement of charge. From now onwards, right, we will start calling it as conduction current. So the current that we are normally aware of it, right, what do we call it as? Conduction current. The conduction current is because of what? Because of the movement of charges. So here we are going to bring in a new term called as what? Displacement current. And this displacement current, right, is it a real current? It is a notional current. What do you mean by notional current? It is not like, when I say displacement current is, say for example, in some particular case, I will say displacement current is 5 amperes. Okay, so we will get this kind of a result, imagine. Does not mean that, in the region where we say displacement current is there, 5 coulomb of charge will be going per every 1 second, not like that. Okay, so this is a notional idea, it is not a real current. Now let us again take the same example. So we have the capacitor plates. This is basically what we call as an charging circuit. What do we call it as? We call it as a charging circuit. And it is a very simple setup to understand the concept of this displacement current. Okay, so when we have the charging happening, what we will be able to observe is the capacitor plates, right, whatever the charge that is there will not be constant, it will change with respect to time, isn't it? The capacitor plates charge will not be constant. Charge will be changing with respect to time. In the circuit, right, there will be a current. As I said, from now onwards, we will start calling it as what? Conduction current. You can see, even I am using this notation IC. What is the notation? IC. Okay, some textbooks, they will even call it as just I. Some textbooks, they will call it as what? Just I or IC. IC means what? It represents conduction current. Okay. So what we can see is this conduction current, how it is related to the charge on capacitor plates. I will be equal to what? dq by dt. The rate at which the capacitor plates are getting charged, isn't it? Current in the circuit will be equal to what? The rate at which the capacitor plates are getting charged. Because we are looking at what? Situation where the capacitor plates are getting charged. Okay. So let us keep it as equation 1. This is what will be our conduction current. Okay. Now in the region between the two capacitor plates, there is an electric field. What is there? There is an electric field. Okay. Now how we are going to understand this displacement current? The displacement current is a term that we are using to explain the relation between the electric field and the magnetic field. Okay. So if you look at the electric field in the region, what is the electric field formula? Q by A into epsilon naught. Okay, so Q will be, at that instant, if you are taking the charge as small q, right, it will be what? Q by A into epsilon naught. Okay, since we are taking the charge at the given instant is what? Small q. So this is what is our electric field. So this is the electric field. Of course, electric field also will be what? Changing with respect to time, because charge is changing means electric field also will change with respect to time. Okay, now what is the electric flux through this area? So the entire capacitor plate, right, has got how much area? A. We can see that electric field and area vector. Area vector means how do we take it? We will take it normal to the plane, right? Area vector, we will take it normal to the plane. Okay. So the electric flux will be equal to what? Area into the electric field value. Because normally flux is what? E dot A, right? Here, electric field vector, area vector, both are in the same direction. That is why it will be what? E into A into cos 0. Cos 0 is 1. Okay. So we can see A and A will get cancelled. What is it? Q by epsilon naught. What is this? Q by epsilon naught. Okay. Now, when we look at the d phi E by dt, rate of change of electric flux. What is it? Rate of change of electric flux means what? We have to take a derivative of this, right? What is electric flux? Q by epsilon naught. We have to take a derivative of it. Derivative means what? Anyway, that epsilon naught is a constant. So derivative of this means what? 1 by epsilon naught into dq by dt. This is what is the rate of change of electric flux. What is this? This term is rate of change of electric flux. Okay. Now what we'll do is we will just take this epsilon naught to the left hand side. Okay, I'll tell you why are we doing all this rearrangement, because we are trying to understand how we will arrive at the relation between the electric field and the magnetic field. So if you take this epsilon naught to the left hand side, right, what we are going to get? Left hand side will be what? Epsilon naught into d phi E by dt. What about the right hand side? It is nothing but dq by dt. Okay. Just keep this as what? Equation 2. So what are the equations we are having? First equation. First equation is what? First equation is for the conduction current. First equation is for what? It is for the conduction current. Okay. What is the conduction current value? dq by dt. Second equation, we are getting the same value dq by dt in terms of what? In terms of the electric flux. We are getting the same value dq by dt in terms of what? In terms of the electric flux. What is that value? The dq by dt value is equal to what? Epsilon naught into d phi E by dt. What is it? Epsilon naught into d phi E by dt. Okay. Now we will bring in the concept of the displacement current. So I'll erase some part of it. So this is all the derivation to arrive at the displacement current value. Okay, Shyam, you are asking question, is the source DC or AC? Okay, so this is a DC. Okay, it's a battery basically. Okay, So we'll just do the conclusion step. So we got two equations, right? What are the two equations we are having? First is the equation for the conduction current. Second is what? The same dq by dt value in terms of electric flux. Okay. Now what we are going to do is just focus on one capacitor plate. Just take one capacitor plate. Okay. So this side of the plate, what is there? There is the wire. The left hand side of the plate, there is what? Wire. Right hand side of the plate, so let us say that I am focusing on the plate 1. Right outside of the plate, there is nothing. What is there? Actually, there is an electric field. Right hand side of the plate, there is what? Electric field. Okay. Left hand side, there is an current. What is that current? We are calling it as conduction current. We are calling it as what? Conduction current. Okay. Now when we look at the magnetic field, left hand side there is a current. Magnetic field is produced by what? Current carrying wire. That much we are aware of. The magnetic field is produced by what? Current carrying wire. Okay. Now what we will do is we will be taking, just to give you a little bit more clear representation, so I'll just draw with a different. So whatever is the capacitor plate area, right, we will take a loop which will be equal to the, which will be like, you know, the boundary of that loop will be what? The boundary of the capacitor plate. The boundary of the loop will be the boundary of the capacitor plate. So we'll consider a loop like that. We'll consider a loop which will have the boundary exactly matching with the boundary of the capacitor plate. Okay. Now through this loop, if you want to find what is the magnetic field at each and every point of that loop, okay, because of the wire is carrying current, right? So what will be the formula that we can use? Ampere's loop rule, right? Integral B dot dl is equal to what? Mu naught into I. What is this I? The conduction current. This is on the left hand side. Left hand side of the plate, right? What is the Ampere's loop rule formula? Integral B dot L is equal to what? Mu naught into I enclosed, right? If you take a loop, means the line integral of magnetic field is equal to what? Mu naught into current that is going through that loop. That is what is the Ampere's loop rule, right? So we apply the Ampere's loop rule on the left hand side. We'll apply the Ampere's loop rule on the left hand side. Okay. Now what we'll do is we will take a loop which is again matching with the boundary of the capacitor plate just on the right hand side. We'll take a loop which is again matching the area of the capacitor plate or the boundary of the capacitor plate on the right hand side. What will be the loop rule? If you try to apply the Ampere loop rule there, what will be the thing? So RHS side, we'll try to apply the loop rule. So what is it? We'll have same integral B dot dl, okay, is equal to, we should have what? Mu naught into I. But is there I here? There is no current. So what we are going to get? We are going to get mu naught into 0, like that. We are going to get what? Mu naught into 0, right? Because the right hand side there is no current. You look at the loop, through the loop, is there a current going through the loop? There is no current, right? Because in the region between the two capacitor plates, this side there is another plate. In the region between the two capacitor plates, there is no current. Means here in the formula Ampere loop rule, we should be putting what? 0. But the thing just now we discussed before, right, is what people were finding that in the region between the two capacitor plate there is a magnetic field. Not only that, if you take the loop which is having the periphery of that loop matching with the boundary of the capacitor plate, right, what is observed is the field at any point on this loop is equal to field at any point on the other side. The magnetic field value, right, on the left hand side is equal to the right hand side. But if you try to apply the loop rule, means what are you getting there? On the right hand side, if we are trying to apply the loop rule, means it should be what? Integral B dot dl is equal to mu naught into current, right? But there is no current. We have to put 0 there. This is a contradiction. What we are able to see is, experimentally, left hand side there is a magnetic field, right hand side there is a magnetic field. If you take loops of area or boundary matching with the boundary of capacitor plate, right, what we are able to observe is magnetic field on the entire part of the loop will be what? Same on LHS as well as RHS. LHS, we are able to apply the Ampere loop rule equation straight away. Integral B dot dl is equal to mu naught into current passing through that loop is what? Conduction current. That is what we are calling it as. But right hand side, when you try to apply, what you are having, right hand side the loop, there is no current going through the loop, so we should be putting mu naught into 0, but this is a contradiction, right? If there is a b value, integral b dot dl cannot be 0. Then how do we adjust for this? This is where the concept of displacement current is introduced. There is no current there actually. On the right hand side of the plate, there is no current. But when we are trying to apply the Ampere loop rule, we always are used to what? Keeping integral b dot dl is equal to mu naught into current. That is what we are used to. But here, right hand side, there is no current. Then how are we going to adjust for this? How are we going to adjust for this? If you look at it, what is the equivalent term? What is the equivalent term for the IC? Because the right hand side also, what we must have here, we should have a term, we should have a current term like that, which from now onwards we will call as displacement current. In the right hand side, when we look at that Ampere loop rule formula, mu naught into something should be coming, right? The term that is going to come there should be equivalent to current. We are going to call from now onwards was what? That is going to be called as the displacement current. The term whatever we are going to keep, we will call it as displacement current. And this value, because the LHS magnetic field is equal to RHS magnetic field, right? What we should have is this current in the mu naught into I term should be numerically equal to the current over there on the right hand side. So what is the term that is equal to, because IC is what? dq by dt, right? What is the term that is equal to dq by dt in terms of the electric flux? What is the term? Epsilon naught into d phi e by dt. So the right hand side, the Ampere loop rule is modified. So what is the equation we are going to use? Integral b dot dl is equal to mu naught into, what is the term we are going to keep? Epsilon naught into d phi e by dt. This term is numerically equal to what? dq by dt. So the continuity of that magnetic field is ensured. LHS part and RHS part, when we take the loop that is exactly matching with the boundary, the magnetic field should be same, right? So whatever is the term that you have here, this is nothing but what? dq by dt. The value is equal to dq by dt. Here also the value must be equal to what? dq by dt. What is the dq by dt value? Epsilon naught into d phi e by dt. Okay. So this term that we are keeping here to ensure the continuity of the Ampere's loop rule, right, is what we will be calling as the displacement current. Now the displacement current value we have derived by taking a simple example. We took the example of a capacitor plate. Okay. But remember, in first chapter, right, when we want to derive the energy stored in electric field, we will use the capacitor plate concept. We will find the energy density in the region between the capacitor plates. What is the energy density value for an electric field? Half into epsilon naught into E square, right? That formula we will derive for the region between capacitor plates. But in general, wherever there is electric field, what is the energy density associated with the electric field? The energy density associated with the electric field will be equal to what? Half into epsilon naught into E square. Similarly, here in a region where there is no current and still we are able to observe the magnetic field. Why the magnetic field coming? The magnetic field is coming because of the changing electric field. The magnetic field is coming because of changing electric field. But how do we quantify it? And how do we, represent it in a way that we are used to? We are used to the idea that, always when there is a current, that current is going to produce the magnetic field. That is what we will see through the Ampere's loop rule, right? Ampere's loop rule, what is it? You take a loop, across the loop you do a line integral of the magnetic field, isn't it? That value is equal to what? Mu naught into the current passing through that loop. So which means we are straight away telling that if you have a current passing through that area, then that can give rise to magnetic field. That idea is what we are using in the Ampere's loop rule. Okay. Now, the new concept that we are seeing here is magnetic field can be produced even if there is no current. Because of the changing electric field, the magnetic field can be produced. But we want to arrange it in a way that we are convenient with. So what is that way that we are convenient with? By using the Ampere's loop rule. So Ampere's loop rule will now get modified. How it is going to get modified? We are going to introduce a new term. The new term, right, is going to account for, what is it going to account for? It is going to account for the magnetic field that is getting produced because of the changing electric field. And we are going to introduce it like a current term. We are going to introduce like what current term in the right hand side of the Ampere's loop rule. Okay. And what is the term going to be called as? We are going to call it as displacement current. But is it a real current? Is there actually a current between the two capacitor plates? There is no current. But the term that is equivalent is what? Epsilon naught into d phi e by dt. What is the term that is equivalent? Epsilon naught into d phi e by dt. Okay. So we will be calling this particular term as the displacement current. What are we going to call it as? Displacement current. Now using this displacement current concept, right, we are able to bring in that changing electric field that can give rise to magnetic field. That is a phenomenon that is observed. But we are able to bring in that idea also into the law or the rule that we are already familiar or that we are already using. What is it? The Ampere's loop rule. The only change is we are going to bring in one more current term from now onwards. What is that current term? We are going to call it as a displacement current. What is the value of that? Epsilon naught into d phi e by dt. Okay. So the displacement current, when we use the relation between the changing electric field and the magnetic field, we have to explain it by using the concept of displacement current. So what is it? We can see normally what is the Ampere loop rule? Integral B dot dl is equal to mu naught into I. So from now onwards, as I said, we are going to call it as what? IC, conduction current. Okay. The magnetic field getting produced because of a change in electric field, right? The Ampere loop rule, we are going to introduce an equivalent term for the current. What is it going to be called as? Displacement current. So what is the displacement current value? Epsilon naught into d phi e by dt. This is what will be the displacement current. And the displacement current, as I said, is a notional current. What is it? It is a notional current. So it is supposed to pass through the entire area of cross section. So what is the area through which it will pass? It will pass through the entire area of cross section. Okay. But is there like a real current that is passing through that? There is no real current. This is the notional current. The displacement current is what? Notional current. Okay. Now look at it. If somebody is taking only a part of this area, because this is where sometimes, we may get questions. So if you take not the full area but only part of the area, we don't take the full area of the plate, we'll take part of the area. Here if you want to apply the Ampere loop rule, we want to apply the Ampere loop rule here. You know what you are going to get? Here the field will not be equal to the B that we are talking about. When we take a peripheral loop, B there will be different. When you take a loop inside, the B will be different. So here let us call it as what? B dash, like that. If you take a loop of smaller area, we'll call it as what? B dash. Now if you do integral B dash dot dl, that is for a smaller loop. That is for what? Smaller loop. Okay. This will be equal to what? Mu naught into epsilon naught into d phi e dash by dt. Because if you take a smaller loop, means look at it, the flux is going to change or not. If you take the full loop which is able to cover the entire plate area, means we are going to get the total flux. But if you take only part of the area, means what? The flux will be reduced. So accordingly the B also will be what? Reduced. Accordingly the B also will be what? Reduced. So the thing that we need to understand, this is more like a MCQ type of question. In the region between the two capacitor plates, right? It's not like magnetic field is constant everywhere. Magnetic field is going to depend on, it will be depending upon what? It will be depending upon the loop size. Means, we can tell it in terms of the distance from the, so if you look at, the center line, If you look at the center line from the plates, right, we look at the center line. How far you are from the center line, how far you are from the center line, okay, the magnetic field is going to depend upon the value, because when you are at the edge, right, edge of that center, edge of that plate, your loop is going to cover the entire plate area. But if you take a smaller loop, means what is going to happen, the flux through the loop will be only small value, so accordingly the B will be changing, okay. So this is another thing that we need to keep in mind. Just like in the conduction side, right, look at the conduction side, this is carrying current, right, we take a small distance, means assuming this is infinitely long wire, it is not infinite long wire, but assume it is infinite long wire. What is the formula for the magnetic field? Mu naught I by 2 pi r, right. If you take a small distance, means what, field will be something. If you take a longer distance, field will be changing, right. So the same way, so we need to look at the idea of field changing depending upon the loop size that is considered, okay. So this is about the concept of displacement current. So what is the key idea from here? When you are trying to apply the Ampere loop rule, the change or modification to account for what? To account for the magnetic field generated by the changing electric field, okay. So what is that term that you are introducing? Displacement current. So if you look at the displacement current value, so the displacement current value that will flow through the region between the two plates, right, that will be equal to the conduction current. The total value of displacement current that will flow through the region between the two plates, right, will be equal to what? Numerically it will be equal to conduction current. So we'll look at it, okay. So what is the proof we are going to do? Prove that if you consider the capacitor circuit, right, whatever is the conduction current that is in the circuit, that will be numerically equal to what? The total displacement current. It's what? Total displacement current. It's equal to total displacement current. So we'll look at the proof. For this, what we'll do is we'll take an capacitor which is having an area A, and Q is the charge on the capacitor at any given instant of time, and D is the separation between the plates. So what are the parameters we are taking? A is the area of cross section of the plates, D is the distance between the plates, and Q is the charge on the capacitor plate at some given time. So this is the setup that we have considered. And what is the current in that circuit? This is conduction current, IC. So if you look at it, right, since charge is changing, what is that IC value going to be? dq by dt. What is the IC value going to be? IC will be equal to what? dq by dt, okay. Now what is the electric field through a region? Electric field will be equal to what? Through the region means we are looking at region between the two plates. Electric field will be equal to what? Sigma by epsilon naught, which is Q by A into epsilon divided by epsilon naught, okay. So Q by A into epsilon naught. This is what is the electric field. What is the total electric flux? We are looking at total electric flux through this area between plates, because here electric field and area both in the same direction. Area vector will be normal to the plate surface, right? So flux will be equal to what? E into A into cos 0. So what is it? E is Q by A into epsilon naught into A. A is cancelled, Q by epsilon naught, okay. So what is this d phi E by dt? D phi E by dt will be what? 1 by epsilon naught into dq by dt, okay, because epsilon is a constant, right? So what is d phi E by dt? 1 by epsilon naught into dq by dt, okay. From here, look at what is the displacement current formula we have got before. What is the displacement current value? Epsilon naught into d phi E by dt, right? What is the displacement current value? It is nothing but epsilon naught into d phi E by dt. Now when we do it, right, what is epsilon naught into d phi E by dt? What is d phi E by dt? 1 by epsilon naught into dq by dt. This is our displacement current value. So epsilon is cancelled. So what is the displacement current value? dq by dt. Isn't it equal to conduction current? So when you have a capacitor plate setup that is getting charged, whatever is the conduction current at a given point of time, right, will be equal to what? It will be equal to the total displacement current through the region between the two capacitor plates. Again I am mentioning, the assumption is what? Displacement current we assume to flow through the entire cross section area. But is it a real current? It is not a real current, it is a notional current. It is a notional current, okay. So here the displacement current we are talking about is what? It is the total displacement current that will flow through the entire area of cross section of plate. If you have a plate like this, right, this displacement current is flowing through the entire area of cross section of plate. What is the relation? the total displacement current that will flow through the entire area of the plate, because remember we are taking the flux through the total surface. We are taking the electric flux through the total surface. Okay, so the capacitor kind of circuit we have, right? The conduction current value will be numerically equal to what? Total displacement current that will go through the region between the capacitor plates. Okay, so this is an important result. And just to summarize the Ampere's circuit law in the modified form. So what is the modified form? If you look at the left hand side of the region between capacitor plates, left hand side. Okay, so what is the form that we are using? Integral B dot dl is equal to mu naught into I, or we can say mu naught into IC. Okay, so here also we can just change it as what? IC. So we'll say mu naught into I or mu naught into IC. That is what we are using on the left hand side. Okay, right hand side, what is the form that we are using? Integral B dot dl. Right hand side means here. What is the form we are using? Mu naught into epsilon naught d phi E by dt. Then only we have the continuity of the Ampere's loop rule. But if you want to look at overall function, right? The overall function will be what? Through a region, when we want to apply the Ampere loop rule, the Ampere loop rule will be by including both these terms. This is what we are going to call as the modified Ampere circuit law. Okay, so what is it going to have? It will be having the right hand side, right? Left hand side is same. Integral, line integral of B dot dl will be equal to right hand side is what? Mu naught into IC plus that mu naught into epsilon naught into d phi E by dt. So which means what? We are having mu naught into IC plus mu naught into ID. So essentially what is the modified Ampere's circuit law form? It is what? Line integral B dot dl is equal to what? Mu naught into IC plus mu naught into ID, which is mu naught into IC plus ID. This is the modified form of the Ampere's circuit law. Now the thing that we need to consider is when we take this equation and apply it on the LHS. Look at this equation, we will apply on the LHS. When we are applying on the LHS side, right? LHS side will only have integral B dot dl. We look at applying on the LHS part is equal to mu naught into IC is there. But LHS, remember, we keep saying this. If you have capacitor plates outside the region of the capacitor plates, if you have capacitor plates, electric field is only going to be there in the region between. Electric field is going to be there only in the region between the capacitor plates. Outside, what is electric field? Zero. This side as well as other side also. What is electric field? It is going to be zero. So which means in the LHS, electric field itself is not there. Which means what will be that ID value, because displacement current is what? Epsilon naught into d phi E by dt, right? When the electric field itself is not there, then what will be the displacement current value? Zero. So LHS side, when we are applying the equation, we are going to have the displacement current as what? Zero. RHS side, when you are applying the equation, right, the modified equation, integral B dot dl is equal to mu naught into RHS side, conduction current is zero. With RHS side there is no conduction current. RHS side there is only what? The notional current which we are introducing as what? Displacement current. That is coming because of the changing electric field. Okay, so the equations when we are using, right, the modified equation, what we need to be keeping in mind is it is not like every time we are going to have IC value and ID value. Some places we may have both, some places we may only have one. Okay, and in some places we may have none. So when we don't have displacement current and the conduction current, what it means, in that region there will be no magnetic field. Okay, so this is about the modified Ampere's circuit law. So looking at the scenarios, right, like I said, if you have steady electric field in a conducting wire, like we have talked about, okay, if you have a conducting wire and there is an steady electric field, means what? The electric field is constant, which means the electric flux will be what? Constant. When the electric flux is constant, what it means? Displacement current will be zero. So when you have steady electric fields, that means what? The displacement current is going to be 0, because the electric field does not change with time. So when that displacement current comes, because look at the displacement current formula, epsilon naught into d phi e by dt. This will come only when the electric field is changing. Okay. Now in the capacitor plate case that we saw, right, charging capacitor plate, what we observed, there is both conduction current as well as displacement current, where LHS side, or the region outside the plates, what we have conduction current. Inside the plates, or the region inside the plate side, what we have displacement current, like that. In one region we have conduction current, another region we are having what? Displacement current. And in most of the cases, right, we may have both displacement current as well as conduction current, both may be present. Okay, why? Because if you look at most of the substances that are carrying current, right, they will not be perfectly conducting, neither perfectly insulating. See, perfectly conducting means what? Electric field is 0, because inside the conductor electric field is what? 0, right? Perfectly insulating means what? Conduction current is 0. Perfectly insulating means what? Conducting current is 0, right? So we will neither have a perfectly conducting material nor will have a perfectly insulating material, which means we are going to have both. We will be having both the displacement current, because displacement current is linked to what? Electric field, right? So we are going to have displacement current. If it is not a perfectly insulating medium, means what? We are going to be having some conduction current, because if it is perfectly insulating means no current will go through it, conduction current will not go through it. Okay, but since majority of the substances, right, they will neither be perfectly insulating nor be perfectly conducting, right, we may end up having both the displacement current term as well as the conduction term to be present. And in some cases, right, like, you know, if you look at the regions through space, etc., if you look at the region through space, there will be no conduction current. So if you look at the region in space, right, when we cover a large distance or large area, we may see that there will be no conduction current, but still we will be able to see the magnetic field getting produced. How the magnetic field will get produced? It will get produced because of a time varying electric field. Because of time varying electric field, right, we will see that the magnetic field is getting produced. And how do we account for the time varying time varying electric field, right? We will be accounting it in terms of what? Displacement current only, no? We will account it in terms of displacement current. So in space, when you are looking at what is the reason for the magnetic field coming into picture, right, even though there is no okay, so when we look at the region in space where we are able to see magnetic field existing, even though there is no current through that area, right, because in space we may not see a current, the conduction current may not be there, but still the magnetic field might get produced. Okay, because space itself, even through the large parts of the space where there is no medium or material, anything right nearby, we may still see that there is going to be a magnetic field that is getting produced. And one of the reasons that is attributed is what? The time varying electric fields. So time varying electric fields can produce what? They can produce magnetic field. Okay, and this is about the idea of the displacement current, and how more than displacement current, right, how we will be able to look at the other side of relation. Faraday's law gives one side. What is it? How a changing or varying magnetic field can produce electric field. Here, through displacement current concept, we are able to understand the other part of the story. What is it? How a changing electric field can give rise to magnetic field. This is practically observed. But we are able to quantify it by using the idea of the displacement current. Okay, now we'll quickly try to solve this question, and then we will be able to understand little bit more about the displacement current. Okay, so the displacement current idea is this much only. Okay, In fact, I mean, on the displacement current, right, the only thing that we need to keep in mind is one, the formula for the displacement current. What is it? Epsilon naught into d phi E by dt. That is one. Second is with regard to the capacitor charging combination. When a capacitor is getting charged, that particular circuit, right, the total displacement current that will go through the entire area of the capacitor plate will be equal to the conduction current value. Now this particular question will help us to understand the displacement current concept in a little bit better manner. Okay, so parallel plate capacitor with a plate area A and a separation between them D is charged by a constant current I. So it is getting charged. Okay, consider a plane surface of area A by 2 parallel to the plates and drawn symmetrically between the plates. So we are considering how much area? A by 2 area, which is parallel to the plates. Find the displacement current through this area. So if you have to put it right in very simple terms, look at this. This is what is our circuit. Okay, so here the conduction current is given as what? I. And we know there is going to be the electric field between the region of the two plates. What will be the electric field value? Electric field is equal to what? It will be, if the charge is Q, Q by A into epsilon naught. A is the total area of the plate, total area of the capacitor plate. Okay. Now what they are asking us? They are asking us, take a plane surface of area A by 2 parallel to the plates. Means, look at this. We will have to take it here. What is this area going to? A by 2. What is the area here? The area is what? A by 2. They are asking, what is the displacement current through this area? First, we should know what is the flux through this area, right? Since we are using phi E as the total flux through capacitor plates, let us use it as what? Phi E dash. What is the flux through this area? Flux through this area will be equal to what? It will be equal to area of this particular region, which is what? What is this area? A by 2. A by 2 into electric field. What is electric field? Q by A into epsilon naught. So A is cancelled. What is it? Q by 2 epsilon naught. That is the flux through this particular area. Okay. And what is the displacement current formula? What is the displacement current formula? It will be equal to what? It will be epsilon naught into through this region. What is the flux here? Phi E, right? Dash. So epsilon into d phi E dash by dt. Okay, we have to just take this particular value for the flux. So which means what? Look at it. The displacement current through this area, let us call it as id dash, will be equal to what? Epsilon naught into 1 by 2 epsilon naught dq by dt. We are taking a derivative of this. Here 1 by 2 epsilon is constant, right? So dq by dt. So this is what? Half into dq by dt. This is our displacement current through that area A by 2. But what is the relation between charge and the conduction current? What is the relation between them? The conduction current is nothing but equal to what? Rate at which the capacitor plates are getting charged. I is equal to what? dq by dt, right? Means dq by dt is equal to what? I. So what is this value going to be? Half into I. So through the A by 2 area, what is the displacement current? It is what? I by 2. If we consider the total plate area, right? Through the total plate area, how much displacement current will go? I. How much displacement current will go? It will be I, right? So what we can see in simple terms is displacement current is proportional to area, isn't it? If I is the displacement current, because the total displacement current through the entire plate area, right, will be equal to the conduction current. This is going through area A. How much displacement current will go through area A by 2? Because our the area we considered is what? A by 2 area, right? It is going to be like a proportion. It is going to be like what? Proportion relation. Okay. So this is how we look at the concept of okay. This is how we look at the concept of displacement current. Okay, so what we'll do is in the next session, right, we will start with a couple of more problems on the displacement current. So here just look at the formula for the displacement current and in what way this is being used. This is being used to account for magnetic field getting generated because of a time varying electric field. So that is what is the role of the displacement current. And one more thing is it a real current? No, it is a notional current. So when we say displacement current is through the region between the plates, it is not like really there is a current flowing through the region between plates. It is a notional current. Okay. So we'll see in the next session, guys. We'll start with some more problems, and then we'll be getting into the Ampere's modified equations. That is a very small part, and we will even start with the propagation or the theory of propagation of electromagnetic waves and properties of the electromagnetic waves. We'll see you in the next session.